It began as a faint shimmer, lost in the static of the deep sky. No alarms, no cosmic fanfare, just a dim speck gliding through the void, barely visible even to the powerful mirrors of Mauna Loa's Atlas array. Yet within weeks, that anonymous fragment, catalogued as 3I Atlas, would turn from a data point into one of the most confounding objects ever observed crossing our solar system. The latest images, captured between late September and mid-October 2025, were meant to confirm its trajectory as it curved toward perihelion. Instead, they revealed something no one was prepared to see. Its tail, once faint and predictable, fractured into delicate threads, each moving as though choreographed by invisible tides. In several filtered frames from the VLT and JWST's MIRI instrument, sections of its coma seemed to flicker, not from sunlight but from within. Brief, localized bursts of reflectivity, unlike any known cometary scattering. At first, astronomers suspected an optical artifact, perhaps interference from cosmic rays or calibration noise. But the pattern persisted across multiple instruments, at multiple wavelengths. The light wasn't random. It followed a rhythm, an irregular pulse, softer than the flicker of a dying star, yet consistent enough to demand explanation. And then came the spectrum, dominated not by water vapor as expected, but by a surge of carbon dioxide and cyanide compounds, unusually pure and steady, even as the nucleus appeared to fragment. Every molecule told a story of extreme cold, of birthplaces beyond the reach of our sun's formative influence. We were watching something unravel, something ancient, fragile, and utterly alien to our local physics. And as the images streamed in from observatories across both hemispheres, one realization began to crystallize. This visitor wasn't just passing through. It was revealing the hidden chemistry of another star's infancy, right before disintegrating in our skies. When the first enhanced composites arrived at the European Southern Observatory, researchers noticed an unsettling pattern. The tail of 3I Atlas wasn't just expanding, it was bending toward the sun. That shouldn't happen. Typical cometary dynamics dictate that solar radiation pressure pushes dust and gas away from the light source. But here, a thin, bright countertail, what astronomers call an anti-tail, was growing in defiance of that rule. To understand it, they overlaid polarimetric data captured by the Gemini North Telescope. The results deepened the mystery. The light scattering from the dust grains showed a highly negative polarization, meaning the reflected light was oriented in a way never before documented for any known comet. The particles weren't behaving like normal silicate or carbon dust. They were denser, smoother, and possibly metallic in composition. It was around this point that the team began comparing the observations to the archives of Oumuamua and Borisov, the two prior interstellar visitors. Oumuamua had been oddly inert, reflecting sunlight like a slab of polished rock, while Borisov had been volatile, rich with water and cyanide. 3I Atlas, however, broke the symmetry. It seemed to combine traits of both, and then added new anomalies. At a distance of nearly 5 astronomical units, roughly the orbit of Jupiter, its coma began outgassing. That's unusually far for carbon dioxide sublimation to dominate. Most comets require the heat of 3 AU or less before they awaken. Yet here it was, glowing in infrared like a living ember before even crossing Saturn's orbit. JWST's spectroscopic readouts confirmed the dominance of CO2, but also revealed something subtler. Faint traces of cyanogen compounds with unusually narrow emission bands, implying that they hadn't been significantly altered by solar radiation. In other words, 3I Atlas carried pristine material, untouched since the early days of its parent star system. What startled researchers even more was the motion of the fragments that began separating from the nucleus. Rather than following ballistic trajectories, the smaller clumps appeared to decelerate, almost as if encountering resistance in a medium that shouldn't exist. No model of solar wind or outgassing pressure could replicate the exact curvature seen in the latest frames. Some scientists proposed that the fragments contained highly reflective ices, with sublimation jets firing in opposite directions, creating rotational drag. Others speculated that electromagnetic interactions might be playing a role, that perhaps the dust carried an unusual charge balance capable of interacting with the sun's magnetic field. But the most haunting observation came from the JWST's October 20th dataset, a subtle shift in spectral color, oscillating in intervals that matched the object's rotation period. A slow heartbeat of light and shadow, repeating with impossible precision. And as those readings reached the analysis teams across the world, one unsettling question began to surface. What could make an interstellar object breathe in light? In the sterile quiet of data rooms across the globe, astronomers stared at the rotating light curves trying to reconcile the physics. Every 3.5 hours, the reflected spectrum of 3I Atlas shifted, not gradually but sharply, like a flicker in a mechanical pattern. This wasn't a simple albedo variation from irregular shape. Something about the surface itself was changing as it turned, as though layers of ice and mineral were alternately catching and absorbing sunlight. At first, the team modeled it as a tumbling nucleus with multiple reflective planes. But when the shape reconstruction algorithms ran, they returned to form too complex to explain. A long, fractured body with shallow ridges running along its length, edges that appeared to glint in the exact rhythm of the observed oscillations. The rotation rate had also begun to slow. That was the most telling clue of all. Natural outgassing can change a comet's spin, yes, but only slightly, and almost always in one direction. Here, the deceleration was rhythmic, consistent, and growing stronger over time. The inference was astonishing. 3I Atlas might be shedding momentum through a recurring release of volatile gases, as if its core were layered in pockets of trapped pressure, venting at precise rotational alignments. It was then that researchers at Caltech noticed something unprecedented in the mid-infrared data. During the brightest intervals, the object's thermal signature spiked, but not uniformly. The warmth radiated from discrete patches along the surface, each only a few hundred feet wide. These patches seemed to awaken and fade cyclically, synchronized to the same rotational phase as the spectral flicker. This observation forced a radical hypothesis. The nucleus could be covered in a crust of mixed ice and dust, cracked into a mosaic of fissures that exposed deeper volatile reservoirs as it turned. Each exposure might trigger a brief surge of sublimation, a flash of gas and light, before sealing again under the freezing void. But there was a deeper implication. If 3I Atlas truly hailed from beyond our solar system, these bursts weren't random chemical fireworks. They were records of another world's environment, frozen for millions of years, and only now reacting to our sun's energy for the first time. Each rotation, each flash was a chemical memory, an echo of a distant star's nebula breathing across time. The conclusion was humbling. This object wasn't simply reflecting light. It was responding to it, transforming visibly with every turn. And as telescopes locked on to its final approach toward perihelion, the question shifted from what is it made of, to something far more profound. What story of cosmic birth is it trying to tell us before it disappears forever? The story deepened when the JWST's NIR-SPEC instrument captured a narrow sequence of spectra during the perihelion approach, only days before October 30th, 2025. The light from 3I Atlas no longer fit the expected emission profile for a carbon chain-depleted comet. The CO2 signature remained strong, but there was a new band, an asymmetric trace of cyanide radicals, dancing in and out of the readings as the object rotated. For a moment, astronomers wondered whether this was an artifact caused by solar flare interference, but the pattern was too synchronized, too deliberate in its appearance. The more they analyzed, the clearer it became that 3I Atlas was undergoing a rapid compositional transformation. This wasn't just sublimation, it was structural collapse. The high-resolution images from the VLT showed a faint halo forming around the primary nucleus, a mist of debris expanding slowly and then stalling, as if something were holding it together. In the thermal data, the temperature along the fragmentation edges rose above prediction by nearly 15 degrees Fahrenheit. That shouldn't have been possible at its current distance. A likely explanation emerged: internal crystallization. As the frozen gases deep inside the nucleus restructured under heat, latent energy released in microbursts, each one enough to jolt loose fragments and shift the object's spin. The fragments that broke away weren't random chunks of dust. They appeared to be sheets, like peeled layers from a frozen onion, each radiating a slightly different albedo. But even this model couldn't account for one impossible observation. The anti-tail, previously a thin ray of counterflowing particles, began to split in two. One strand followed the sun's gravitational curvature as expected. The other moved erratically, like it was influenced by magnetic fields or charged plasma flows. The polarimetric data confirmed a strange deviation, an excess of left-handed circular polarization, a trait rarely seen except in specific crystalline structures and metallic compounds. In essence, 3I Atlas's debris was reflecting light as if it contained ordered molecules, Not the chaotic aggregates of dust and ice we find in typical comets, but something more uniform, perhaps even layered by temperature gradients formed in an alien nebula. The astronomical community fractured overnight. Some argued it was just an extreme case of volatile depletion and cosmic weathering. Others began whispering that this might be the most pristine interstellar sample ever recorded, a window into chemistry predating the sun itself. And as the JWST prepared for one final observation before perihelion, everyone knew this would be the defining moment. If the object survived its closest approach, humanity might finally glimpse the untouched architecture of a foreign star system. But if it didn't, we'd only have fragments of light left to interpret what was never meant to be seen. On the morning of October 30th, the world's observatories held their breath. 3I Atlas reached its perihelion, just over 1.4 astronomical units from the sun. The expectation was straightforward. The intense radiation and thermal stress would either ignite a surge of outgassing or tear the object apart entirely. But what they saw instead was eerily tranquil. Through the JWST's NIR cam, the interstellar traveler appeared suspended in perfect balance. Its coma glowed with a faint bluish-white haze, more reflective than before yet strangely stable. For the first time since its discovery, there was no violent jetting, no unpredictable brightening. The structure looked deliberate, almost calm. The fragmentation had ceased. The nucleus, though diminished, held together like a shard of polished ice enduring the heat of a star it had never known. Astronomers initially suspected the object had exhausted its volatile reserves, leaving behind an inert carbon core. But then came a subtle shift, an oscillation in brightness so faint that only after stacking hundreds of JWST frames did it become visible. It pulsed once every 7 minutes, not strongly, not symmetrically, just a delicate shimmer, like a breath barely held. This recurring shimmer coincided with a measurable change in its rotational velocity. The spin rate, which had been decelerating for weeks, began to stabilize. Some hypothesized that the object had reached an equilibrium between sublimation torque and solar pressure, an exquisitely rare balance point. Others believed this flicker might mark the final expulsion of buried gases through microscopic fractures that now stitched the surface. At the same time, the Hubble Space Telescope caught a phenomenon no one expected. Faint radial shadows extending ahead of the nucleus, as though it were projecting its own spectral halo forward into sunlight. That optical mirage, caused by differential scattering of CO2 and cyanide ions, produced what appeared to be an outline of the object's original form, ghostly and symmetrical. It looked less like a dying comet and more like the memory of one, reflected in solar wind. Scientists compared the readings to laboratory simulations of dust aggregate evolution under intense radiation. None could reproduce the subtle order of its tail's geometry. The grains seemed aligned, oriented in a single direction, as though organized by some quiet natural magnetism beyond our modeling. In that moment, every telescope, from Chile to Hawaii to space itself, was gazing at the same fragile traveler from another sun, holding itself together against annihilation. And then, within hours of its closest pass, the brightness curve dipped sharply. 3 Atlas began to fade, not exploding, not disintegrating, but dissolving into a trail of particulate mist. A silence spread through mission control rooms across the world. The object had crossed the threshold, but what it left behind would soon challenge everything we thought we knew about interstellar matter. By November's first week, 3II Atlas was gone from visible light. What remained was a ghostly filament stretching across millions of miles, faintly luminescent in the ultraviolet. The object had not shattered in a single event. It had evaporated in sequence, layer by layer, as if its inner structure were programmed to dissolve in phases. JWST's final data packets revealed that even after the nucleus disappeared, its chemical footprint lingered. Ions of CO2, cyanogen, and carbon monoxide drifting in parallel lanes that refused to disperse as ordinary comet tails do. That persistence drew attention. In normal solar coma, radiation pressure scatters ions rapidly, stretching them into diffuse arcs. But 3I Atlas's remnants clung to formation, a ribbon of coherence that seemed magnetically aligned. Magnetometers aboard the Parker Solar Probe detected minute disturbances in the solar wind precisely at the region where the debris field passed. Subtle ripples, like a whisper moving through plasma. The alignment lasted for days. Some scientists proposed that the particles were carrying remanent magnetization, fossilized magnetic signatures from their system of origin. If true, this would be the first tangible evidence of an interstellar magnetic field preserved in solid material, a message frozen in dust, billions of years old. Spectral analysis of the fading trail added one final twist. The relative abundance of CO2 to cyanide had shifted dramatically since perihelion. The cyanide bands grew stronger as the object faded, implying that the outer layers had been depleted of volatiles, but the core, what little remained, was chemically richer, more complex, and possibly more organic than expected. Theories began to diverge. One camp argued this was merely thermal stratification, different ices evaporating at different temperatures. Another group, however, noticed something stranger. The isotopic ratios of carbon and nitrogen didn't match any known pattern within the Milky Way's local neighborhood. They were heavier, skewed by nucleosynthetic processes typical of older, metal-poor stars. That meant 3I Atlas, likely formed in a system far older than our Sun, perhaps on the outskirts of a long dormant star cluster that has since dispersed into the interstellar sea. Its journey across the galaxy might have taken hundreds of millions of years, until a chance gravitational encounter sent it toward us. And as its final molecular traces faded into the background of solar dust, one realization spread among the observing teams. We had witnessed the complete life cycle of an interstellar relic, from arrival to disappearance, in real time. Yet the data refused to close cleanly. Some measurements, particularly those involving polarized light, showed inexplicable periodic spikes long after the nucleus was gone, almost like a heartbeat still echoing in the light. What exactly was still pulsing in the void where 3I Atlas used to be? Weeks after the disappearance, the mystery deepened. The JWST's instruments, scanning the same region for calibration purposes, kept detecting faint periodic brightening in the infrared, a whisper of warmth where nothing should remain. These flashes occurred precisely every 3.4 hours, matching the rotation period of 3I Atlas before its dissolution. At first, this was dismissed as sensor noise, a ghost echo from data processing. But then, independent confirmations arrived from ground-based observatories in Chile and Hawaii. The pulses were real. That impossible rhythm forced researchers to rethink what the debris field actually was. Could microscopic fragments of the nucleus still be rotating coherently, preserving the same angular momentum the parent body once had? Theoretically, yes, but only for a few days before solar wind dispersion erased all organization. Yet these pulses persisted for weeks, as if something unseen held the fragments together in resonance. One explanation gained quiet traction among physicists: electrostatic cohesion. In the vacuum of interplanetary space, dust grains charged by ultraviolet light can interact through faint electromagnetic coupling. If 3I Atlas's material had an unusually high conductivity, say, due to embedded metallic or graphitic compounds, it could sustain a self-organizing field for longer than expected. The fragments, in that case, weren't separate at all. They were part of a plasma-bound cluster, gently oscillating in unison, still echoing the motion of their vanished nucleus. It was a haunting image. The ghost of a world, held together by invisible forces, fading slowly in the light of a foreign sun. As weeks passed, the residual light curve finally began to smooth, merging into the solar background. But even as the signals faded, the data continued to yield revelations. When astronomers modeled the isotopic ratios from the debris, they noticed peculiar enrichment in nitrogen-15 and carbon-13, signatures that pointed to formation in an environment rich in cosmic radiation, possibly near the galactic halo. That meant 3I Atlas wasn't just old. It might have originated in one of the Milky Way's earliest planetary systems, a fossil from an epoch when carbon chemistry was still new to the cosmos. The philosophical weight of that realization was staggering. We weren't merely observing a fragment of another world, we were witnessing the chemical ancestry of life itself, encoded in the remains of a comet that had traveled across time to disintegrate within reach of our telescopes. Every measurement, every flicker of light became a message. Life, as we know it, might not have started in isolation. The seeds of organic chemistry, cyanides, carbon chains, frozen gases, were drifting between stars long before Earth even existed. And as that truth began to settle, one question lingered in the hearts of every scientist who watched 3I Atlas fade into nothing. If these seeds came from the stars, how many other fragments like it are still traveling, unseen, waiting to brush past our sun? Now, only the data remains. The object that once glimmered against the black sea of interstellar space has dissolved completely, its remnants scattered beyond the reach of light. Yet in its disappearance, 3I Atlas left something far greater than a trail of dust. It left a question imprinted on the human mind. How many times has the galaxy whispered to us, and how many times have we failed to listen? When astronomers review the images, the faint threads, the rhythm of light, the unexplainable order in chaos, they see more than numbers. They see a bridge between stars, a reminder that our solar system is not isolated, but immersed in an ocean of ancient travelers. Each one carries the fingerprint of a forgotten world, each one a capsule of matter that predates the Earth itself. Perhaps what we witnessed was not a comet's death, but a kind of cosmic transmission, a release of chemistry and memory into the winds of another star. Maybe this is how the universe communicates, not with words, but with dust, with ions, with fragile structures that cross the abyss to dissolve into our light. As the final observations faded into the archives, humanity was left with a paradoxical feeling, loss intertwined with awe. Something unimaginably old had touched our corner of space, offered us a glimpse into its origin, and vanished again into silence. Do you believe 3I Atlas came to show us the truth of where we began? Or was it just another passing ghost from the stars? Tell me what you think below.